Well, healthcare buildings are the second most energy intensive facility type in the US, and especially large consumers of natural gas. Today, healthcare represents almost 20% of the US national economy, 10% of US carbon emissions, and 5% of global carbon emissions, and it's growing. And rather than doing no harm, healthcare is actively fueling the carbon fire. This is a big chunk of emissions with a huge opportunity to reduce energy, among other emission-causing activities within healthcare. So over 75% of the natural gas used in a hospital is reheat energy, which is a function of high ventilation rates in hospitals. And this is regardless of location. Heating loads are largely similar across the country. We believe that hospitals are using 30 to 40% more natural gas than is necessary to meet the air quality standards for occupant comfort and safety. Air change rates being used for ventilation design in hospitals can be traced all the way back to the late 1800s, during the time of Florence Nightingale, who advocated for designing hospital wards with natural ventilation or outdoor air as a mean of infection control. And you can look back at the research and the values that were used to trace back to 2 air changes. Since then, 2 air changes has been a staple in the ASHRAE and California ventilation codes throughout the years. But the key of this is that there's no scientific basis for air change rates. Air change rate, in our opinion, is the wrong metric for air dilution. Air change per hour could mean that if you raise the ceiling from 8 feet to 9 feet, that you have to increase ventilation. But it's really more about the source of the infectious particles and diluting that. Air change is really meant to simplify, but engineers designing hospitals should be using science to determine ventilation levels, not using a rule of thumb like air changes. One big finding really showed the massive energy reduction benefit of VAV systems compared to constant volume systems. This was the nation's first hospital air quality study, which uncovered a ton of data that will be publicly available for further studies, but our analysis alone uncovered a few things. Main conclusion was that there was no discernible relationship between ventilation rates and air quality contaminants within the ranges that we measured. And we expected to see at some point where the theoretical curves would show up in the data, and they didn't. Another finding is that at 2 air changes, the air was just as clean as it was at 12 air changes. An analogy that my co-author uses often is you can take 2 showers a day or you could take 12 showers a day. At a certain point, you just aren't getting dirty enough for those extra showers to matter. And that's really what we're saying here with air changes. The air is just not getting dirty enough for additional air changes to matter. The result is wasted energy with not a lot of ventilation benefit. We also proved that ventilation could be done without return boxes in California, which was previously not allowed by code. One other finding of this study uncovered the myth between clean and less clean areas. The California code requires spaces like clean linen and med prep rooms to be positive pressure, indicating that they're considered to be clean, but the air quality in those rooms and the adjacent less clean rooms were the same. This would seem to indicate that those rooms don't necessarily benefit from a positive pressurization, and the pressure requirement could be removed in future code changes. A NR, or no requirement, for those spaces would allow them to become VAV, which would reduce overall energy consumption for those spaces as well. The additional benefit in energy savings and cost savings, our project was projected to reduce nearly 95,000 therms, or 29% of the boiler energy at the North Tower of South Bay Medical Center. This was 21% of the total natural gas consumption of that tower. This brings the EUI of the facility from a 298 to 231, which is a savings of 67 kBTU per square foot per year. The project also is projected to save 2.8 million kWh of electricity, or 25% of the total electricity consumption of that tower. So these projections show an annual cost savings of nearly $460,000 a year and a carbon emission savings of over 2,460 metric tons of carbon dioxide equivalent. That's the equivalent of 539 passenger cars being removed from the road each year. Looking at extrapolating that data through California, we took the number of hospitals in California with some assumptions based on existing conditions and which hospitals would have the similar opportunities. And we estimated that this is an economic opportunity of $2.5 billion worth of energy savings and a total decarbonization value of $14.5 million metric tons of carbon dioxide throughout the state, the equivalent of removing over 4 million cars from the road. So this is significant. Reheat energy is the single largest energy use in a hospital, and that extrapolated throughout the state and also the nation could have massive impacts towards decarbonizing healthcare buildings. The reaction has been very positive, and I'd say we've had more interest and curiosity in the details of our study more than we've had critical reactions. I think once the California Energy Commission publishes the study, a lot of those questions can be answered. Healthcare organizations and many of our clients are reaching out to find out how they can implement lower ventilation rates to save energy. We've had a lot of our clients that are leaders in decarbonizing their healthcare buildings, supportive of future code changes and wanting to get involved in that effort. One of your follow-up questions about changes to building or code requirements, OSHPD has actually made a change in the 2019 version of the California Mechanical Code to remove the need for return boxes in spaces without pressure requirements, which essentially makes VAV easier and cheaper to do in a retrofit project. So this is huge for retrofitting existing hospitals throughout California, in that many of those hospitals have the opportunity now to do this with controls only, without large capital and without a lot of disruption. And this can be done very quickly with a controls contractor and an air balancer. That is a huge step in the right direction. OSHPD also removed admin and other non-patient zones from the air change tables and now allow designers to design these spaces based on ASHRAE 62.1, where those spaces are designed based on area and occupancy. We had a client who wanted to do 12 air changes per hour in every patient room after COVID-19. We worked with them and we changed air distribution designs and showed that reduced ventilation rates could achieve the same benefits. And I think this study was pivotal in changing their minds and opening up that possibility for them. Yeah, I did see that. And that was an interesting recommendation. I think there's a big difference between air changes and equivalent air changes in the definition. Equivalent air changes could be achieved with an in-room filtration device or even by opening a window. Hospital codes use air changes per hour for ventilation requirements. Those suggestions could still be aligned with our recommendations, but we really can't compare air changes per hour with equivalent air changes. It's not the same metric. So comparing the number 5 with our recommendation of 1 or 2 air changes isn't really comparing apples to apples. What our study shows is that the indoor air environment within a hospital is incredibly clean. Looking at the particulate data from air changes, from 12 air changes down to 1 air change, the air is very clean and doesn't really get anywhere close to the action levels, the levels that we set that would increase ventilation to satisfy those air quality conditions. But regardless of the recommendation, our study really poses the question of, is using air changes the right method to defining ventilation codes? Well, filtration is a well-understood method of cleaning air, and it doesn't have to be fresh outside air to be clean from infectious particles. Filtration accomplishes that just as well. Equivalent air changes is a way of saying that it's either outdoor air or clean inside air. Clean air is clean air. Our study suggests that real-time measurement of air quality could be a good way of measuring, but our measurements were so low that it didn't seem that it was going to be cost-effective during the course of our project. Our study showed that in hospitals, there's so much dilution already that there really wasn't a benefit of real-time air quality monitoring. Air quality measurements will help develop the actual required airflow levels rather than relying on a rule of thumb. And I think that's ultimately the way that the code should go. I think both are equally important. The bigger opportunity will probably vary from hospital to hospital based on how the systems are designed, how big the critical zones are compared to non-critical, how sophisticated the controls are. Is OR setback even possible with the current systems that a hospital has? And also the geographical location. ORs in hotter and humid climates may demand more energy to satisfy conditions than in more mild climates. What the current ventilation rates are for those different types of spaces. The non-critical zones in some cases may be easier to implement changes and realize savings faster. Those savings can then be leveraged to get projects done in critical zones where you need more support from surgeons and other clinical staff. So it's really a situation of the support you have within your organization to get those projects done and how supportive the leadership and those clinical staff will be